Live stream for Physics 232. Today we're going to be talking about DC circuits and going into Kirchhoff's rules and Kirchhoff's laws, and we're going to do a bunch of problems to figure out kind of how resistors work in DC circuits, as well as actually analyzing two different circuits using Kirchhoff's rule to find the currents, voltages, and everything we need to find there using those. So let's get started here. We're going to talk a little bit about how resistors work in a DC circuit. So in DC circuits, if we have resistors in series, we start off resistors in series. And I should probably actually start off with my usual pasting some links for the Learning Center's Facebook, Instagram, and to the Learning Center, as well as an attendance sheet into the chat window. I'll paste that attendance sheet at the end as well. So definitely check those out if you get a chance, and fill out that form so we let your teacher know that you've come. So getting back to it, resistors in series. So if I were to draw a circuit, I'm going to draw a power source with a positive side here. And we're going to draw 3 resistors in series. That means they're going to be in line with each other, one after another. I'm going to go down after another. So I can call this one R1, R2, and R3. And to find out the resistance of the entire circuit, we can add up those resistances. So that's R total is going to be equal to R1 plus R2 plus R3. This works fairly similar to how we talked about capacitors and how to add them up in parallel. It's the same idea as capacitors. It's just we're doing the opposite thing. So in series for capacitors, we added up 1 over the capacitance and took the inverse of the sum of all of those. Here, we're adding up all of them in series for the resistance, and the resistance is additive as it goes through. For resistors in parallel, drawing that circuit out, we can see, so I'm going to draw 1 resistor there. It's going to go down. And we're going to have another resistor there and another resistor there. Again, calling this R1, R2, and R3. So we add this the same way we would add capacitors in series, where the R total is going to equal, let's say 1 over the R total is equal to the summation of 1 over R1 plus 1 over R2 plus 1 over R3. So you can see, and I like to write this out as R total is equal to the same thing, R1 plus 1 over R2 plus 1 over R3, but then just take that whole thing to the -1 power. By taking it to the -1 power, we're basically taking the reciprocal of this guy here, so we can just find that resistance, because that's really what we want to find. So this is kind of the formula I use to find the total resistance of resistors in series. And you'll notice, excuse me, if we put numbers in for all of these, resistors in series, you're going to get less. So we're not really adding them up. We're taking like fractions of those resistance. We're splitting up the current between all of these different paths. So we end up with less resistance that way. With resistors in series, we're going to end up with more resistance. We're going to be adding them all together. So it's 2 different ways we can control the resistance of the circuit. Let's try a problem out. So this one asks, what is the largest and smallest resistances you can obtain by connecting these 3 resistances together? So to draw that out, basically the same idea. The largest would have to be adding them together. So we can get the largest possible value by adding all three of those values together. So there'd have to be a series circuit. That's a terrible looking resistor. There we go. So if I said that this one's 44 ohm, this one's 42 ohm, oops, HM, and this one's 294 ohms. And it doesn't matter which order we put them in because we're adding them all together. And once you look at the math of it, the commutative law of addition says we can move those numbers around. So 44 ohms plus 42 ohms is the same as 42 ohms plus 44 ohms. So it doesn't really matter. But the total resistance, in this case the max resistance, is going to equal that 44 ohms plus 42 ohms plus 294 ohms. And if I were to get rid of all that and go here, we can get a new calculator up. We can add those values together. So to add those, 44 ohms plus 42 ohms plus 294 ohms. It's equal to 380 ohms. And we know it has to be the maximum because if we were to put any of those in parallel, even combinations of series and parallel, anytime we put two of them in parallel, we're going to get a smaller value than both of them. But if we put them in series, we're going to increase the resistance. So that said, to find the minimum, we'd want them in parallel. And they'd all have to be in parallel. So to do that, I could draw the three of them like I did before. And say this one is 44 ohms. Let's use omega. This one's 42 omega, or ohms, and this is 294 ohms. And to find the resistance at the minimum, so let's say R min, that's going to equal 1 over 44 ohms plus 1 over 42 ohms plus 1 over 294 ohms. We can plug that guy into our calculator. 1 over 44 ohms plus 1 over 42 ohms plus 1 over 294 ohm. But I have to take that whole thing to the power of -1. I didn't write that on there, but I'm going to. And that gives us 20.02 ohms. So we got to make sure we take this to the -1 power because we're flipping it around because all of this in here is equal to 1 over our total. But we want to find out what that total resistance is. So that's 20.04 ohms. So this one up here is obviously the max. It's much bigger than all of them combined, or it's the size of all of them combined, or bigger than any of them individually. This one, if you notice, is smaller than any of them individually. It's smaller than the 44. It's smaller than the 42. In fact, if you were to take two resistors that have the same value and put them in parallel, the total resistance would be half of it. Because if I had, say, 1 over R plus 1 over R, that would equal 2 over R. When I take the reciprocal of that, it's R over 2, so we're halving the resistance by doing that. So anytime those resistors are the same value, you're going to get half as much resistance by putting them in parallel. You would get twice as much resistance putting them in series. When the resistor values change, then obviously that's where we go and do our calculations like that. But it's a pretty easy calculation to make. We just have to kind of know the relationship with it and kind of plug in and use the right values. So now let's look at a problem here. This one uses power. So we have three different devices in this case. We have a toaster, an electric frying pan, and a 72-watt lamp. So I must be using one of those old incandescent bulbs. So they're all plugged into the same outlet with a 15 amp circuit. So, and then this gives us the note that the three devices are in parallel when plugged into the same socket. So we want to draw a circuit diagram for the toaster, frying pan, and lamp, and label the current passing through each device. So to draw my circuit, I'm going to use just this little circle with a V as my voltage. That just signifies it's some voltage is coming through there. It would probably be 120 volt AC, because that's what comes out of our walls, generally speaking, somewhere right around there. And most of our wall sockets have a 15 amp circuit breaker attached to them. And if we draw a circuit, I'm just going to draw a really simple circuit. I'm going to put a box here. I'm just using these boxes for my different devices. I'll put another box here, and then a third box here. So this one, the first one there is going to be my toaster. Second one is going to be my frying pan. And the third one is going to be my lamp. And we know that this first one is 1840 watts. We know that the frying pan is 1360 watts. And we know that the lamp is 72 watts. So in this situation, we could ask ourselves, well, what's constant? What's changing at different times? And looking at the different circuits that are here, we can see that from this point here to this point here, the voltage, if I put a voltmeter here, I can connect, the voltage is going to be the same. So the voltage anywhere along this line and up to these is the same in reference to this point. So the voltage is always the same. It's always that 120 volts AC. And since the voltage is always the same, we can use the definition of power. So remember, power is equal to current times voltage. And since our voltage is always the same, we can use that to find the current of each device. So I can say the power divided by the voltage is equal to my current. And I can say the total power. Let's go one at a time. So looking at each device, the power of the toaster is going to be equal to 840 watts divided by 120 volts. So I can just do that on here. 1840 divided by 120. That's equal to 15.33 amps. So remember, watts divided by volts is going to give you amps. So 15.33 amps. Looking at the power of the frying pan. Well, that's equal to 1360 watts. We're going to divide that by 120 volts. And that's going to equal 1360 divided by 120. It's 11.33. Well, 11.33 amps. Looking at the final one, the lamp, it's equal to 72 watts divided by 120 volts. 72 divided by 120 is 0.6 amps. So that's the amperage, the current flowing through each of these paths. So this guy here, the toaster, has 15.3 amps going through it. The frying pan has 11.3 amps going through there. And the lamp has, it's going both sides, but 0.6 amps going through there. Now they also want us to ask you, will that 15 amp breaker blow? Because we have 15 amps going on here. And if more than 15 amps is drawn through that circuit, the circuit breaker is going to blow. And it does that to protect the circuit. So if we have too much current going through, you could cause a fire or other things like that. That said, in this case, we want to see, is there more than 15 amps? So we can find that by adding up all of these values, but we can already see based off of that, which is 15.3 amps, and that it's going to be more than that. But then we can ask ourselves, how much is the total amperage there? So taking these numbers, we have 0.6 plus 11.3 plus 15.33 is 27.26. So it's about 27.27 amps total, which is a lot more than the 15 amp circuit we have. So even if you had a 20 amp circuit, it would probably still blow the circuit breaker. Let's look at another problem. Here it wants us to find the equivalent resistance between points A and point B, where R is equal to 5 ohms. So this circuit here, kind of a weird circuit. We've got this connection going on in the middle, and we have 2 rows of resistors going through there. I'm going to redraw this circuit a little bit, because points C and D, to me, those are really the same point. Right? They're connected together. Their voltage is going to be the same going through there. There's going to be some current that maybe could go back and forth between them. But really, since there's no resistance to it there, there's not really going to be much of a change. I can draw this same thing kind of like this. That was a poorly drawn resistor. That's better. All of these have the value of R. So really what I have here is 2 groups of resistors, and within that group the resistors are tied together in parallel, but between the groups they're tied together in series. So if I call this one group 1 and this one group 2, we can see that group 1 is in series with group 2. If I call this one, say, little a, little b, little c, little d, we can see that resistor A and B are in parallel to each other, and resistor C and D are also in parallel with each other. So to find the total resistance of this circuit, what I really want to do is kind of add up the resistors in parallel first, and then take the sum of both of them in series. And in this case, all of the resistor values are the same, 5 ohms. So as I was saying earlier, I know that the resistors in parallel, so RAB, this is group 1 really, is going to equal 1 over 5 ohms plus 1 over 5 ohms. I'm going to take the inverse of that. Going here, 1 over 5 left out my, yep, there it is, plus 1 over 5 ohms. I want to take the inverse. We get 2.5 ohms. You see that the resistance really halved there. We have half as much resistance as either one of those resistors in between. And then looking at the second circuit, R C D. So that's that combination. We want to add those two, resistor C and resistor D, in parallel. Well, that's going to be the same thing, right? Because they're all the same value. So we know that's going to equal 2.5 ohms. Now the total resistance will be these two resistor values added together. So 2.5 ohms plus 2.5 ohms, which is just equal to 5 ohms. So ironically, you could get this same circuit if you just took one of those 5 ohm resistors and did that. The only difference between it might be the amount of power consumption, because different resistors are rated at different powers. So here you might reduce the amount of current going through each resistor, which reduces the wattage power that's being consumed by each one. As long as you had a resistor that's powerful enough to take the whole current going through, should be good. But that's the answer. You got 5 ohms of resistance going through that circuit. Now we're going to dive a little bit into Kirchhoff's laws. So Kirchhoff's rule, he has two basic rules for circuits. The first rule is what we call the junction rule. Let me zoom in here. So the junction rule says it's the sum of all currents entering a junction must equal the sum of all currents leaving the junction. So what that means is if I had a circuit and there was a junction point, and kind of this one goes up this way, this one goes down this way, so our connection splits at one point, and my current's flowing in this direction here. The current here and here would split out that way. If I called this one I3, this one I2, and this one I1, this would say that I1 needs to equal I2 plus I3. You can also say that the summation of all of them, I1 minus I2 minus I3, is equal to 0. Which is how I like to look at it. The total amount of current at every junction should be 0. So the in is positive, the outs are negative, and we get a total summation of 0 there. Okay. Or you can write it like this, is the easy way to do it. And you can think of it as kind of what comes in must come out. So all the current going into a junction needs to exit that junction, and it's kind of split up. But it's not always split up evenly. It's split up based on the resistance of each branch of that current. There's also a loop rule. So the loop rule says the algebraic sum of charges in potential around any closed circuit let's say path or loop, which is why it's a loop rule, must be 0. Or we can say this as the summation sub I of all the voltages is equal to 0. And what this basically means is for every positive voltage you have, every electromotive force, every voltage supply you have, which is usually on a positive voltage, you can then calculate and go around any loop. And every time you hit a resistor or some load on the circuit, we can find the voltage drop across that resistor. So it's the current times the resistor gives you the voltage drop. And as we go around those loops, the total voltage drop should equal 0 along any loop, essentially. Should sum up to the same as the voltage source, essentially, and equal 0. And we'll go through a few examples here going forward. But those are the two Kirchhoff's rules and laws. Using these two rules, we can create a system of equations for our circuit to identify the current at any point along the circuit, because usually we can control the voltage going in at power supplies and we can control the resistance values. But looking at the current is always kind of a questionable thing. We don't always know what the current is for everything. And we can use this rule to then find out those currents. And sometimes we know the current at one place, but we're missing the voltage. And for every unknown variable we have, we need to make an equation using either a loop or a junction to identify what those are. And for every equation, I guess for every unknown variable, we need an equation. If we have the same number of equations as variables, we should be able to solve that system of equation through a series of substitutions, essentially. And we're going to go over a few of those here. So this is our first circuit here. So notice this circuit has a voltage supply here and a voltage supply here. There's 3 resistors in the circuit, and it tells us the current of one of those, but not the current of the other 2. So we need to identify kind of what we have, what we don't have. We don't know this voltage. We don't know these currents. But we do know this voltage, we know the rest of the resistor values, and we know that current there. So we need at least 3 equations. And there's 3 different loops I can see in here, plus basically 1 different junction. There's 2 junctions, this point and this point, but they're really going to tell us the same thing. So really we're looking at 1 junction point equation and 3 different loop equations we can do. So I'm going to go ahead and write down the first loop I see is kind of going this way around the circuit. So if I were to make it, starting at V1, going up this way and following around down through the middle circuit there, the middle here, we're going to have kind of that loop going there. The second loop I see starting here, I like to start at voltage supplies if I can, and going around that way. And the third loop is kind of the whole thing. So going all the way around and back to here. It's doing that full loop all the way around that circuit. Those are the 3 big loops that I see. And then we have this 1 junction here. I'm going to label it in blue. So we can create equations based on Kirchhoff's laws for these. So for that junction, we can say that the current going in, so say I1 is equal, I guess I1 plus I2, right? I1 plus I2 is equal to I3. And we can say that because this is going into the circuit, this is going into the junction, that one's going into the junction, but this one's leaving the junction. So that means that the 2 currents going into that junction needs to be equal to the current coming out of the junction. We can also, for that purple loop that I defined, I can start at V1 and say that V1 minus I1 R1, that's this value here, plus going down now this way, we're adding I2 R2 because our direction of our loop is going the opposite direction of our current. So instead of having a voltage drop across this resistor, we're actually gaining voltage in this case. And that is going to all equal 0 because there's nothing down on this part of the cycle here. So that full loop down there should give us everything across that loop should equal 0. And looking at the green loop, I can see that V2, that's V2 here. I'm going this way. And as far as the voltage supplies go, we could always draw a line from negative to positive. And if our loop is in that same direction, then it's going to be a positive voltage. If our loop's going the opposite direction, we're going to have a negative voltage for that voltage supply. In this case, it's positive because those are in the same direction. We can say V2 minus I3 R3. And in this case here, we're going in the same direction as the current now. So it would be minus, say, I2 R2. And that should equal 0 because there's no resistors on the top here. So that's just the same current going through. There's no voltage drop going. So I've got 3 equations now. I don't need to use this big outer loop in here. I could write it out if I wanted to, and you could use that in place of these other 2. I'm going to write it out just to be thorough. I'm going to say V1 minus I1 R1 plus V2 minus I3 R3 is equal to 0. So notice it's V1, which is here, minus R1 I1 going around plus V2 minus I3 R3 is equal to 0. So now it's about plugging in the values that we do have here and solving for our system. So I'm going to start by plugging in values into our purple loop here. Let's go to purple. Let me say that V1, which we don't know, minus, and I'll say this is 2 amps times 12 ohms, plus I2, which we don't know, R2, which is 6 amps, or 6 ohms, I'm sorry, is equal to 0. Now we can simplify this a little bit because we can multiply the amperage times the resistance, and we can say that V1, I'm going to solve it also for V1 while I do this, is equal to 24 volts minus I2 times 6 ohms. So I just moved the I2 6 ohms over to the other side. That's why it's negative now. And then our amps times our ohms is going to give us a positive value. Okay, so I'll move this guy down, give me a little bit more room. So now I have this equation here where I've solved for the ohms, essentially. But we don't know what I2 is just yet. So we can solve at this point and go to our green equation here. I'll move that way down. So now plugging in the values we know for this, V2 was 21 volts. That was a given. We can subtract from that I3. R3 was 5 ohms. We can subtract from that I2 times 6 ohms. 6 ohms. And that's all going to be equal to 0. So I'm just plugging in the values they were giving us here. And here up top I have this equation in terms of I2. And then down here I have this equation in terms of I2 and I3. So I actually am going to rewrite this bottom equation in terms of I3 alone. So I'm going to rearrange it a little bit while I do that. Maybe not. So again, this is going to be 21 volts minus I3 times 5 ohms minus. Now I want to get rid of this I2. To do that, I really need to plug in a value for using this equation up top here. So I3 is equal to that. Let's rearrange it so we can say I2 is equal to I3 minus. We know what I1 is. That's 2 amps. So I can plug in now the 2 amps here. And then I'll substitute in this I3 minus 2 amps times our 6 ohms is equal to 0. So it's just a lot of different substitutions using the 3 variables we have. So now I have the second one down to just two variables. So now I can actually just solve for I3 on the bottom. Solving for I3 now, we can distribute this negative 6 here into this here. So we get 21 volts minus I3, that's a 3, times 5 ohms. We're going to minus I3 times 6 ohms. And then we're going to distribute that negative through as well. So we're plussing 2 amps times 6 ohms is going to be 12 volts. So this needs to be 12 volts in there is equal to 0. Now we can combine our terms here and here. 12 volts plus 21 volts is 33 volts. And we can combine our terms here and here, the two I3 terms. So that's a negative 6 and a negative 5 ohms times I3 was a negative 11 ohms times I3, which is equal to 0. Moving that negative term over to the other side of the equation, we get 33 volts is equal to 11 ohms times I3. And then to solve for I3, we can divide each side by 11 ohms. So 33 divided by 11 is 3. So we end up with 3 amps, because volts divided by resistance in ohms is going to give us amperage is equal to I3. So we know that I3 has a current of 3 amps there. And notice we haven't even used this equation yet. Since we only have 3 unknown variables, we can get away with just using these 3 equations up on top. So plugging in 3 amps here, I can say, up to the right that is, I2 is equal to our 3 amps minus 2 amps. So I can see that I2 is going to be equal to 1 amp. So now I have the current there. I can plug that value into this purple equation to solve for my voltage. So voltage 1 is going to equal 24 volts minus, we know it's 1 amp. So I'm going to plug in 1 amp here times our 6 ohms. And 1 amp times 6 ohms is really just 6 volts. So 24 volts minus 6 volts. So I say V1 is equal to 18 volts. So of the 4 equations I had to use 3 of the equations because I had 3 unknown values. And in doing that, I solved that V1 is equal to 18 volts. I2 is equal to 1 amp. So this guy here is 1 amp. And I3 here is equal to 3 amps. And we can see that makes sense because we have 2 amps going in from I1 zooming in here. There's 2 amps going in here. There's 1 amp going in there. And there's 3 amps coming out there. So 2 amps plus 1 amp is 3 amps. So that all follows Kirchhoff's rules, and we were able to use those to solve the equation. So let's try another one. This other one's a little bit more difficult. So we still have 2 loops. We still have 2 power supplies in here. This is giving us the direction of the loops. I'm going to draw my colored circles on here. I'm going to do the same. This time I'm going to use orange for this one. And here they give us the voltage supplies values. They're giving us all the resistor values, but they don't give us any of the current values. So we also have that junction here. I'm going to put that in blue again. So we're going to use that junction and those 2 loops that they have inside to find the values that we need. So breaking this down, looking at the current junction first, we can see that I1 is going to be equal to I2 plus I3. And we can see that because I2 is going out, I3 is going out, and I1 is going into this junction B. We can also write the equation for the purple loop here. We can say V1 down here minus R1 I1, that's up here, minus R2 I2 is equal to 0. And this time our current in this middle one is going downwards, the same direction as our loop. Because they're in the same direction, we have a voltage drop across this resistor. Last time our current was going up instead of down, so it was going the opposite direction of our loop. That's why we added the the voltage of that resistor. Here we're dropping that voltage down. Doing our orange loop, I'm going to write this a little bit lower. That's going to be a negative V2, just get at the bottom of that, plus R2 I2, so that's this one here. And we're adding, so now we're going the opposite direction of the current, so we're going to add that as a positive voltage increase. Going across the top, we would then subtract I3 R3. Then going down the right side, we're going to subtract R4, I4, or I3 again. Because this has the same current. This current flows all the way down at around through here. And that's all going to be equal to 0. Okay, so now we can plug in the values that we know. Let's start with the orange one. We have 29 volts for V2, so that's going to be negative 29 volts. We've got 3 ohms for R2, so that would be plus 3 ohms I2 minus, I'm going to write the resistor values first, so 3 ohms again times I3. And then R4 is 4 ohms minus 4 ohms I3 is equal to 0. Since we have 2 terms that have I3 in it now, we can combine those terms together. So 3 ohms plus 4 ohms, both of them being negative, gives us a negative 7 ohms. So I can write this now as negative 29 volts plus 3 ohms I2 minus 7 ohms I3 is going to be equal to 0. Now we want to solve one of these, either for I2 or I3, just so we can plug it in to another value that we have higher up. In this case, I'm going to solve for I2. keeping the positive value on one side and putting the negative values on the other side. That's going to be 3 ohms times I2 is equal to 7 ohms times I3 plus 29 volts. And that gives us now a value to substitute in. So going up towards the top, we see I have this term here where I know the voltage. I don't know the currents of either one, but I've solved this bottom equation for I2 in terms of I3. And over here, I have I1 in terms of I2 and I3. So, starting out with I1, I can say that's equal to, I have to divide down here, this orange equation. I have to divide everything by 3 ohms to get I2 isolated. Forgot one step. So I2 is going to be equal to 7/3. The ohms actually cancel out, times I3, plus then 29 divided by 3. I'm just going to write that 29 over 3. But voltage divided by voltage divided by resistance is going to equal current, or amperage. So I'm going to write that as amps. So that's a value we have now of I2 in terms of I3. I'm going to use that for this blue equation and substitute that in. So that's 7/3 I3 plus 29 over 3 amps plus I3. Oops. And then I can combine the like terms of the two I3s. So I1 is going to equal, in this case, it's really just I3 is like 3 over 3. So we can combine those terms with common denominators. So that's 10 over 3 I3 plus 29 over 3 amps. So now I can substitute my values of I2 and I1 into this purple equation. And we know what the voltage is. So the voltage is 24 volts. Right? We're going to be subtracting. We know what the resistance is. That's 3 ohms times our I1 value, which is going to be 10 over 3 times I3. I wanted to write that in blue so we can see that substitution. There we are. Plus 29 over 3 amps. So that's from I1 minus R2 being 3 ohms, times I2. I'm going to run out of space here. So let's move this guy down here. So I2 is 7/3 times I3 plus 29 over 3 amps. So, here we are. So I want to multiply that times 7/3 I3 plus 29 over 3 amps. And that all should equal 0. So I'm just substituting in for I2 and I1 into this equation. Now this whole equation is in terms of I3, so we can just solve for I3. It looks kind of complicated with the fractions in there, but do notice that all the fractions have a 3 in the denominator, and now we're multiplying by 3 ohms. That does make it quite simpler. So mathematically, the 3's can all cancel out. And when we multiply that ohms times amperage, we get voltage as well. So just following this, it's going to be 24 volts minus 10 volts plus 29 volts. Oh, I left out the so this should actually be here. So that's going to be 10 ohms, because we're just multiplying that ohms in times I3 plus 29 volts minus, again, the 7, oops, that should be a negative. So I want to distribute that negative into here as well. Got to watch my signs. Distributing the negative on the second part over here, that's negative 1 ohm times 7. So that's negative 7 ohms times I3 minus 29. And then amperage times resistance is going to equal current or voltage. Yeah, because V is equal to IR equals 0. So now we can add up all the voltages that we have on here and then push all the I3s to one side of the equation. Notice there is negative 10 minus 7. So that's going to be a negative 7 ohm I3. Or sorry, a 17, negative 17 ohm I3. Okay, and if I move that to the right side of the equation, that leaves 24 minus 29 minus 29. So 24 minus 29 is 5. 5 minus 29 should be 24. So that's 24. Did I do that right? Let's see. 24 minus 29 minus 29. Negative 34. I knew I did something wrong. So that's negative 34. Now if we divide by the resistance, so dividing by 17 on each side, 17 ohms, and this was in voltage, we would get voltage divided by resistance is going to give us amperage. That's negative 2 amps is equal to I3. Now we can plug that value in to our other two equations down here. Starting to run out of space, but we can see that I2 is going to equal 7 over, yeah. So that's going to equal 7 over 3 times negative 2 amps plus 29 over 3 amps. So multiplying that across, that's going to be a negative 14 over 3 plus 29 over 3. So common denominators, let's just do a 29 minus 14. So that's going to be 15 over 3 amps, which is equal to 5 amps. And that's for I2. So now we have a value for I3 and I2. Going over to the right here, we can see and solve for I1. So I1 is then going to equal 10 over 3 times negative 2 amps plus 29 over 3 amps. I'm going to move this up just a tad. The nice thing about writing on a tablet is you can manipulate when you run out of room. I can actually resize it. Just a little smaller. So multiplying across, I1 is going to equal negative 20. Negative 20 over 3 amps plus 29 over 3. So adding those together, that's 49. No, adding those together, it's 9 over 3, which is equal to 9 over 3 amps. Which is equal to 3 amps. That's better. So we were able to find the current of all 3 of the chains of our circuit, the branches there, just by using Kirchhoff's rules and those 3 basic equations that we had, the 2 loops and the 1 junction. So Kirchhoff's rules helped us again. Notice that the current of I3 is negative. And I think that's an important thing to recognize, because we thought the current was going in this direction. So when we set up our equation, we assumed, since it's going the same direction as the loop was, so the loop was going this way, the current was going in that same direction, we called it a voltage drop. And notice our math said it's a negative current. The current is actually flowing the opposite direction, this way. And that's shown by that negative voltage that or negative current that we got for I3, this negative 2 amps in there. That's one of the reasons I like this, because the math will solve those problems. So even if you're not sure which direction the currents are flowing, just pick your best guess and set up your equations based on that best guess, and the math will fix it for you. So anytime you set that up and the math says, no, the current's going this way, you can just change your answer. And that's all we have for you today. We've covered Kirchhoff's laws, we've covered DC circuits and resistance and other things. Definitely, if you haven't filled out our attendance sheet, fill out the attendance sheet. I just pasted a link in the chat forum as well. And I'll see you all next week. Best of luck. Oh, also, I have drop-in hours in Pingy. Afterwards, you can also schedule a meeting with a tutor with the links above. So definitely check in if you have any questions with me, myself, or other tutors as well.